they feel, I learned this in Chem 1A, but I might do it a little differently than what your Chem 1A instructor does. And so, since your Chem 1A instructor isn't doing the grading, make sure you do it the way I'd like you to do it. All right, any other questions? Okay, if you didn't get yours back, you can get it back right after. All right, we're going to finish up the nomenclature, and then we're going on to chapter 15 material. We're going to skip 14 right now. So let's take a look at the end of chapter, homework. Also, as a follow-up to the homework for the chemical reactions, you can also ask me in class, too, at the beginning of class or during office hours about any particular reactions you aren't sure if you got the correct answer or not. Okay. I can take a look at that. All right, do you recall which one we left off on for the nomenclature? Okay, let's see. What's wrong with the projector here?
We did amine, hydroxyl, 3.
Okay.
So just 3 days.
Okay.
We're going on to 3D.
Okay, thanks. This was just working this morning. But it's not now. Okay. 3D. All right, so we did 3A, correct? All right, one of the things you'll notice on 3A is this. It's odd that we call this, did we call it the amine first or the aqua first? Amine. It's because it's alphabetical. Why did we do the hydroxyl? Because all these are alphabetical, regardless of short. And so the amine came first, and then the aqua, then the hydroxyl. So there's that amine, aqua, hydroxyl. But why are they written in the exact opposite order? They're written in the exact opposite order. Is that always the case? No, it's not always the case. The way the ions are written in the formula follows a different organizational scheme. And the different organizational scheme is this. The anion ligands are always written first. So below here we have nitrite, which is an anion, and amine, which is neutral. And so the nitrite would be written first in the formula because it's an anion ligand. Whenever we have anion ligands, we write those first. Let's see if there's more examples there. They're easy to show. Okay, this is the case. And so it makes sense. The hydroxyl is going to be written first, regardless of order. And then we write the neutral ligands. Now, the neutral ligands are written in alphabetical order, just like when we name them. When we name these things, we name them in alphabetical order, but when we name them in alphabetical order regardless of charge. And so when we name these, we don't name the anion ligands first, we name all the ligands in alphabetical order. When we write the formula, then the formulas are organized in that, in the anion followed by the neutral. But what alphabetical order? There are two alphabetical order schemes. One is based on the name. So amine versus aqua. Amine, A-M, aqua, A-Q. Amine should have been written first. It's alphabetical. N before Q. But when we look at this, why is amine not written before aqua? Because they're using a different alphabetizing scheme, and that different alphabetizing scheme is based on the first element in the formula. Based on the first element of the formula, this is H, that's N. And so this is why we wrote the aqua before the amine, because they're doing it alphabetical based on formula. First element of the formula. That, that scheme I don't particularly care for. Obviously I should follow the rules, but do you know the rules are governed by a committee, and this committee, they have a hard time agreeing sometimes on things. And sometimes the strongest personality will dictate the rules. And so it was, I think the 8th or the 9th edition of Petrucci, the rules were different. If you go back, some years, and you look back at the nomenclature, it used to be they put the neutrals and then the anions. And then all of a sudden by the 10th edition, they switched it. And then they put the anions and then the neutrals. Why? Because some nomenclature committee decided they wanted to change it. And so what you see bottles of reagents with all kinds of rules back and forth depending on the year, and what was the going trend at that time, or going rules at that time. And so this based on formula is difficult because I have a pen. Because how do you write the formulas? Is there always one way of writing a formula? For example, is acetic acid CH3COOH, or is acetic acid HC2H3O2? Well, this isn't going to be a ligand, but do you see the point? Which one is right, which one's wrong? Well, which one's right? Both of them are right. Which one's wrong? None of them are wrong. These are two perfectly fine, acceptable ways of writing acetic acid. But this one would be ordered according to C, this one would be ordered according to H. But you say, well, acetic acid is not a ligand. What's a ligand might be acetate. Well, acetate as a ligand would be like CH3COO minus versus C2H3O2 minus. And then you go, oh, both of these are C, so no problem there. But what about ethylene diamine? How do you write ethylene diamine? Well, normally we write the formula. This would be what we call the condensed structural formula for ethylene diamine. We have two amines on the end, and then ethylene in the center. So here are the two amines, and here's my ethylene. That's ethylene diamine. So does ethylene diamine begin with an H? But then you go, well, that's the condensed structural formula. Normally organic chemists will begin the formula with a C, so it'd be C2, 2 carbons, ethyl. And then we do CH2, 4, 6, 8, H8, and 2. And then you go, wow, ethylene diamine is not H, ethylene diamine should be C, right? And then you go to this book, and this book will say, no, ethylene diamine is an E. Why is ethylene diamine an E? It's an E because the abbreviation for that formula begins with an E. And so which one do you use? Do you use E, C, or H? Well, which one's wrong? Well, none of these are wrong. All these are correct, right? But it just screwed up my alphabetizing system. Whereas, even though the formulas can be written differently, can the name be arranged? Could I call it diamine ethylene? No, everybody's going to call it ethylene diamine. And so at least the name is consistent, whereas the formulas aren't. We'll often see this, you know. I was looking for ammonia years ago, and I was going to get it from a European chemical manufacturer. And so I was looking, I couldn't find ammonia, and I was thinking, how can they not have ammonia? Ammonia is so common. But I eventually found it. And I found it, and it was written like this, H3N. I was looking for N, not H. And so that's why I couldn't find it. But they had it here, trihydrogen nitride. Actually, they didn't even call it ammonia. Well, anyway, or you could call this nitrogen trihydride. Depends on how you write it. You know, you call this you could call this hydrogen nitride or trihydrogen nitride, or you could call this nitrogen trihydride. You see how it just, well, anyway. So my personal opinion is, and this is the way I've taught it, is, you know, the easiest thing is just to keep the alphabetizing system the same. We just alphabetize it according to name. And so if you were to write it like this, I would have put amine before aqua and just say, okay, amine comes before aqua, therefore I'm going to alphabetize it amine and then aqua. And then just down the list according to name, not formula. And you're going to see variations in how people write the formula. If you do a lot of complexes, water is written H2O or OH2 all the time. You know, a lot of people write it OH2 to show how it bonds, right? Rather than H2O, because the hydrogens don't bond. And so if H2O is written OH2, then all of a sudden it's order, you know, alphabetical. It's just gotten sent to the back of the line. But anyway, you can do whatever, you know, as long as you're consistent. If you order by name, always do that. If you order by formula, always do that, and I'll check it to see that you're consistent. But don't flip back and forth. All right, so this amine before aqua, and then I would have written amine before aqua. But I would have written hydroxo before either of those because hydroxo is an anion. There we have to stay consistent, you know, the anions, because you know, you can't just sprinkle in the anions there. And so we do the anions alphabetically and then the neutrals alphabetically. Okay, let's go on to this one. Now, this is amine, but what is ONO? It's NO2 minus. What is the NO2 minus? Nitrite. But NO2 is an interesting ion. Let's take a look. What makes that interesting? If I have a nitrite, you'll note that nitrite actually has two potential donor atoms, actually three, if we treat the two oxygens separately. And so nitrite is going to have an oxygen out here with a negative formal charge, oxygen double bonded here. This whole thing carries a net negative charge. This is nitrite. Do you guys remember resonance hybrids? When I think about resonance hybrids, these two oxygens are the same, basically, because there's another resonance form, and the actual form is the hybrid. And so I don't see this as a 0 and a negative. I see each of these oxygens as a negative 1/2. And so either one of these oxygens can bind. Actually, can both of these oxygens bind? If I have, let's say I have platinum 2+ here. Can this oxygen bind and this oxygen bind, making nitrite a bidentate ligand? Is that possible?
No.
Why not? Why can't both these oxygens bind to the platinum? Yeah, it would form a four-membered ring with highly strained bonds, okay? 90-degree bond angles, which are unfavorable. So this is going to be a monodentate ligand. So either of these oxygens bind. If an oxygen binds, then it looks like this structure down here. If the nitrite binds an oxygen, then we get this, monodentate. And to indicate that, we write the formula ONO to show the oxygen is actually binding. Because if we wrote an NO2, you might be mistaken in thinking that the nitrogen is binding. And so this is written ONO. But the nitrogen is also a Lewis base, and this nitrogen can also donate a lone pair to the central metal. And so if the nitrogen binds, then it looks like this here, where the nitrogen in nitrite is binding here, and we write the formula NO2. So ONO and NO2 are both the same thing, they're nitrite. It's just showing the difference in binding. It also screws up the alphabetical order because one is alphabetized according to N, the other is alphabetized according to O. They're both nitrite. Now, to indicate the difference in the bonding, since they're both nitrite, you can't tell the difference. I mean, nitrite's nitrite, right? NO2, ONO. Doesn't really matter. And so we're going to add something to the name of this. If the nitrite binds on the oxygen, we call it nitrito-O. And so nitrite, change the ending to nitrito-O-. And so this shows just the nitrites bonding to the oxygen. If the bond is to the nitrogen, we call it nitrito-N. And so let's go ahead and name that complex here. And so here, when we name it alphabetically regardless of charge. And so we just look, this is nitrito-O, this is amine. And so obviously what comes first, amine or nitrite? Amine. Triamine, yep. Trinitrito-O. And cobalt or cobaltate? Cobalt, yeah. When we name them, the metal goes at the end. When we write the formula, the metal goes at the beginning of the word. But this would be triamine, trinitrito-O, cobalt. What's the charge on cobalt? Yeah, the charge has got to be +3 because we got the 3 nitrites at -3, and the whole, that's a neutral molecule, actually. This is what we call a complex molecule, not a complex ion. And so this is a molecule. And so what did we say? Triamine? Amine with 2 M's or 1 M? 2 M's. 1 M would be referring to the weak organic bases called the amines. And so this would be triamine. What did we say? Okay. Nitro or nitrito. You know, if it's like nitrate, then we call it nitro. Since it's nitrite, we call it nitrito. And so that's typically what we'll see. Triamine, trinitrito, -O, cobalt, 3, Roman numeral 3. That's all one word, and that's the name of that molecule. Okay. All right, let's take a look at the next one here. It's a nice black pen. I don't know what happened. But is green okay then? The contrast? All right. Looking at the next one, this is an ionic compound here. We have a complex cation and a complex anion. And so an ionic compound is a 1-to-1 ratio, cation to anion in this case. So they must be equal charge. So let's name the cation first here. What would the name of this one be? Tetra, aqua, platinum. Now the charge platinum occurs as +2 or +4. What should we do? Should we do platinum 4? If we do platinum 4, then could this one be platinum 4 too? So this is -6 from the 6 chlorides, +4 would give us -2. That wouldn't balance. This has to be +2. So if the first platinum is +4 and the second platinum were +2, then this would balance out charge-wise, because this would be 4+, water is a neutral. This would be 2+ -6 gives us -4. So +4 -4 is 1-to-1. Does that make sense? But here, that's wrong, actually. That's wrong. And how did I know I was wrong? I knew I was wrong because of this table. Where was that table again? Here. This table 24.1. What happened to my scroll bars here? Let's scroll over. 24.1, platinum 2+ occurs as 4 or 6 coordinate. 4 coordinate, right? Platinum 4+ occurs as 6 coordinate. This is based on experimental data. And so when I go back to this, I have to use some additional information to answer this question, and that is, what are the charges on platinum? Well, the charges, this is a 4-coordinate platinum because aquas are monodentate. And therefore, this has got to be platinum 2+. This is 6-coordinate platinum, and therefore, this has got to be 4+. And so if this were 2+, this whole thing is 2+ cation. And then we have a 4+, -6 gives us a -2, so it's a 1-to-1. A 2+ cation and a -2. Okay, so those are the charges. So let's go ahead and name this thing completely here. The name of this would be Tetra Aqua Platinum. Are you sure? Is it platinum or platinate? Platinum? How come? It's not platinumate. Platinate. That's a cation. But what's the charge on platinum? Yeah, this is platinum. It's got to be 2+ because it's 4-coordinate platinum. All right, so this is a cation name. Then we need a space. There's got to be a space here, and then the anion name. What's the anion name? Platinum? Platinum hexachloride? Is that right? Platinum hexachloride. Hexachloride platinum? Getting closer. Okay, hexa. Is it chloride or chloro? What is it, chloride or chloro? Chloro. It's going to be hexachloro because anions, we change the ending to the O ending. And so it'd be hexachloro platinum or platinate? Platinate. That's because it's an anion complex. And so hexachloroplatinate, and the charge on this, 4. And so this ionic compound is going to be named tetraaquaplatinum 2 hexachloroplatinate 4. one cation for every one anion. Okay, this one is going to be an anion here, complex. Okay, why don't you take a look at that one and then tell me what you come up with for the name. All right, what did you get for the name of that? What's the name of the next one? Somebody have it? No? Give me your best guess. Diaqua is correct. Aqua before oxalato. So A before O. Diaqua. Dioxalato. Why not bis? Bisoxalato. We don't have to use bis, the alternate prefix system, because there's no di in oxalato. There's no, and so this is fine. We could put the parentheses like this to say that there are two oxalatos. It's fine. So we can do diaqua, dioxalato, bidente. But it's not that necessary. Usually we put parentheses to avoid confusion. In this case, it's not absolutely necessary. You know, and when you go on in science, if it's not necessary, they usually omit it because, you know, every parentheses adds another character space. Another character space when you're printing, you know, thousands and thousands of copies of this adds up to a lot of paper. And so on a lot of scientific publications, they have word limits. You cannot exceed this number of words. You know, people want to write more and more, and it's hard to compress, you know. And it forces people to write much more concisely. You know, whereas if there's an open-ended limit, you can just keep blabbering on about whatever. But anyway, dioxalato, what's next? Ferry, good. And the charge on iron? Yeah, the charge is +3. So that would be the diaqua dioxalato ferrate 3 ion. All right, E here, if we look at that's just a regular cation, not a complex cation, but just a normal cation, silver ions, and a complex anion. And so it's an ionic compound here. And so normally we name the cation first. Let's go ahead and name the cation. The cation would just be the silver ion. Would we call silver, would we call it disilver? Is that correct? Disilver. Or bis silver? Or just silver? Yeah, just silver. Like for example, if we had this one, if we had Ag2SO4, how would you name that, Ag2SO4? This would just be silver sulfate, right? We wouldn't call it disilver sulfate. This same thing. Each silver is a +1. Therefore, HgI4 must be a -2. And so it's just a regular cation and then a complex anion. So let's go ahead. We name the cation silver. Silver is a fixed charge of +1, so we don't need a Roman numeral here. And then what's the anion name? Tetra iodide? Is that right? No, whenever we have an anion, we have to change the ending to O. Iodo. Tetraiodo. Tetraiodo mercury or mercurate? Mercurate. And the charge on mercury? The charge has to be 2. If the charge were 4, then the +4 and the -4 would cancel each other out, and then it'd just be neutral. It wouldn't be an anion. And so this would be tetraiodomercury 2. And so the whole name of that ionic compound, silver tetraiodomercury 2. We're done.
For a 3D,
Uh-huh.
I thought the standard or like the rule was you name anions first and then you name the neutral ligands.
No. No, let me stop you there. When we name it, we ignore charge. We just go alphabetical, all of them. When we write the formula, then we, separate it according to charge. And you go, who thought of that rule? I don't know. To me, it just seems so ridiculous to do it that way because, it'd be just better just to do it consistent the same way and then have people recognize, you don't have to you don't have to move the anions up front as people recognize the anions, And, yeah, so, this is why it'd be nice if the rules were consistent one way and then do the opposite to go the other way. And so to write the formula, you go this way. To write the name, you go the opposite. But unfortunately, it doesn't work like that. To write the name, you follow one set of rules. To write the formula, you follow a different set of rules. Is that weird? It's weird. But I don't write the rules, so it's all right. We just have to follow the rules as best we can.
For 3D, the iron has a charge of 3 plus because oxalate has a charge of 2 minus.
Yeah.
There's 2 of them.
Yeah, and there's 2 of them. Oxalate's written like that, although I don't, that abbreviation's not that necessary. Oxalate is so easy to write, C2O4. But it's a common abbreviation. So a common abbreviation, that writing OX will save 2 characters. Compress the paper down, save paper and cost, printing costs. That's it. And so there are some standard abbreviations that we can use. Whereas ethylene diamine is a much more. Do you know the abbreviation for ethylene diamine? Well, we'll see it in just a minute. Did we do these 2? Did we do 8C? Yeah? You remember doing this? EDTA? Yeah? Yeah, this is a very useful abbreviation because EDTA is a very long name. Ethylene diamine tetra. Well, the anion name itself is ethylene diamine tetraacetate. So you have one ethylene diamine and then you attach 4 acetates to it. Each acetate's a -1, so this whole thing, EDTA, is a -4 anion. But that's the name of the anion. To name it as a ligand, we change the ending. So rather than calling it ethylene diamine tetraacetate ion, we call it ethylene diamine tetraacetate tow. You know, as a ligand. All right, let's name this series here from 12. Did we do these already or not? No? No, okay. So note here, in the formula, the anion ligands are written first. So this is hydroxide as a ligand is called hydroxo, right? Chloride as a ligand is called chloro. So chloro. And so the anions here are written before the cations. If we have multiple anions, they're written alphabetically. According to Petrucci, they're written alphabetically according to formula, but you could just write them alphabetically according to name. That way we're consistent. At least if we're alphabetical according to name both ways, you know, one way and the other, then that's better than being alphabetical according to name in one direction and alphabetical according to formula in the opposite direction. All right, well, that's if we have multiple anions. If we have multiple neutrals, we do the same thing. And so let's take a look at naming this one. How would you name this one? Here. Okay, what goes first? Should we name the anion ligands first or the neutrals? Well, we write the anion ligands first in the formula, but when we name it, we don't pay any attention to the charge, and we write it according to alphabetical order, and this is correct by name. And so amine comes before hydroxo. So this would be pentaamine hydroxo chromium. What's the charge on chromium? 3 plus. And so pentaamine hydroxochromium 3. Do you want me to write that down, or are you okay? Amine, was it 2 M's or 1 M? 2. Yeah. Pentaamine hydroxo, no space. This is all one word. Hydroxo, chromium 3. Roman numeral 3 plus 3 charge. Okay, let's go to this next one here. What is that? All right, the next one here, we have 3 ligands, chloroaquaamine. When we write the formula, we write them in alphabetical order, not the formula. When we write the name, we write them in alphabetical order, regardless of charge. Right? And so which one would go first, chloroaqua or amine? Amine. So this would be triamine, aqua, dichloro, chromium 3. You know, the plus 3 minus 2 gives us plus 1 in that chart.
Wait, why does this one chromium? Why does this one chromate and the last one chromium?
Well, actually, this one was chromium as well, because these are cation. Cation neutral will be just chromium. The one before, like, well, let's take a look at this one
I
here.
thought we said this one was chromate, that's why I'm confused. Was this one chromium or chromate?
Chromium.
Okay, so they're both chromium.
They're both chromium. Do you want me to write that down, or you got it?
So if the entire
Yeah.
compound is negatively charged, that's when you do chromium.
Yeah. So this one would be chromium positive. This one would be chromium positive. This would be chromium positive. This would be chromate because it's negative. This is going to be chromium because it's positive.
So, when you're writing down the name, you write it down alphabetically, regardless of the charge.
Yes. You just ignore the charge, write them down alphabetically. We run into the same issue here. I would have written amine before aqua because I would have just, you know, first we write down the anion ligands in the formula first, alphabetically, and then we write the neutrals first. I mean, neutrals second, excuse me, alphabetically. And when I do alphabetically, I just do it according to name, so amine comes before aqueous. So I would do it in the amines right after the chloro and the aqueous last. You could do it that way. It's just, the only reason is because of how people write formulas. But whatever you do, you could choose to stick with Petrucci by using the first element of the formula for alphabetizing, or you could use my system, which would just be the name. But whatever you do, be consistent. Yeah. How about this one? What's this one called?
EN again?
Yeah, what is EN? EN stands for ethylene diamine. And so that's it. And so this was what we were talking about earlier. Do you do ethylene diamine based on carbon as the first element? Or do you do ethylene diamine based on hydrogen as the first element? Or do you do ethylene diamine based on E as the first element? If there are multiple neutrals, how do we alphabetize ethylene diamine? Well, Petrucci alphabetizes it with an E. Is there an element E? No. Anyway, whatever. We'll just continue here. And so by name, it's no problem. E is the name. And so when we name this, how should we name it? Yes, diethylene diamine. Should we use diethylene diamine? Because if we use diethylene, that's two ethylenes. Diamine, that's two amines. And so it sounds like if we use diethylene diamine, it sounds like we have two ethylenes and two amines. Right? But in reality, we have two ethylene diamines. And so that means we can't use the di, otherwise that leads to confusion, so we should use bis. And so this would be dichloro bis ethylene diamine. So dichloro bis ethylene diamine. The prefix has no impact on its alphabetizing scheme. In its alphabetical order. And so B for bis is totally ignored. E for ethylene diamine is considered.
And then for this, it's just one M because it's...
Yes, this amine is just 1M because it's the weak organic base ethylene diamine. The amine with two M's refers to only one molecule. What is it? Ammonia. If somebody said diethylene diamine, you might think that they have two ethylene molecules and two ammonia molecules. Right? And so that leads to confusion. And so this is why we do bis. And to emphasize that we're talking about two of these rather than two ethylenes, somebody might say, oh, that's two ethylenes and still come up with two amines, right? Especially if they don't know the spelling on this. To emphasize this, here is where parentheses would be quite useful to have in the name, because then for sure this is talking about two ethylene diamines. Right? It's not so necessary in oxalato, but here we don't want it. And so dichloro bis ethylene diamine, and then the metal is chromium or chromate? Chromium, and the charge. What is the charge on chromium? Yeah, 3. That's right, Roman numeral 3. Can I write the formula for ethylene diamine? Yeah. This is the formula for ethylene diamine. You can use that if you want.
So you would never give us like the
Would I write it? Okay, this is also the formula for ethylene diamine, C2H8N2. That's also the formula for ethylene diamine. This is also the formula for ethylene diamine, H2N, CH2, CH2, and H2. Right? This is also the formula for ethylene diamine, CH2, CH2, NH2, 2. Or you could do CH2 parentheses 2 NH2 2. There's different ways of writing the formula, depending on what you want to emphasize.
So you'd be really familiar with these different variables?
Yeah, so rather than writing it like this, you know, I could have written like this, chromium, Cl2, parentheses, now I need 2 ethylene diamines, so I'll write C2H8N2, 2, like that. But, you know, there's a problem with writing it like this. If I write it C2H8N2, do you know what isomers are? Isomers? Isomers are things that have the same formula. Do you know how, like, for example, do you know why I write ethanol like this, C3CH2OH? Write ethanol like this. This is what we call the condensed structural formula. The reason I write it like this is because there are 2 isomers for this. Like, for example, if I did C2H6O, am I talking about ethanol? Yeah, I might be talking about ethanol, but I also could be talking about dimethyl ether. Dimethyl ether has the exact same formula, you know, the exact same molecular formula. And so which one am I talking about? Well, that's the same problem with this. Am I talking about ethylene diamine, or am I talking about some isomer of ethylene diamine? And therefore, that's why I wrote it like this. Because here, clearly, this is ethylene diamine. It's not some other structure, you know, that we can arrange these atoms in. And so, you know, to do this properly, you don't know if that's ethylene diamine, so we shouldn't write it like that. Instead, we should write it like this, CrCl2, and then I write it like this to show, you know, the symmetry of this, H2N, CH2, CH2, NH2. But a lot of people don't like this backwards. And so some people write it as NH2, CH2, CH2, NH2. And so you'll see both of these written. You'll see it written backwards like the H2N. This is actually forwards. Or you'll see it backwards like this to show it's an NH2 group. We have 2 amines, 2 NH2 groups attached to an ethylene molecule. Do you see that? And so this is why I don't like alphabetizing according to the element. Because if we alphabetize according to the element, then this way of writing ethylene diamine is alphabetized according to H. This way of writing ethylene diamine is alphabetized according to N. I don't like the ambiguity in that. I don't know why the committee decided to do that, because this is very commonly done. Writing it backwards or forwards, people don't care. You know, it's like acetic acid. Like, did I already do acetic acid? Did I talk about that? Yeah. It's like that. Acetic acid, do you alphabetize it according to C, or do you alphabetize it according to H, you know? Well, this is the same thing, because these are 2 common ways of writing ethylene diamine. But I'm sure that, you know, these people have their reasons for doing it the way they do it. And maybe I'm just not fully of the negative implications of alphabetizing it according to name. Okay, so that's the formula for ethylene diamine, but you know, it's much easier, and you don't have to, I'm not going to hold you responsible. Although the name, to write the formula is pretty easy if you know what an ethylene group is. In organic chemistry, an ethylene group is CH2CH2, and then you know that we have 2 amines stuck on the end. Well, ammonia is NH3, so we got to get rid of one of the hydrogens and to bond it to a carbon, so this has got to go down to NH2. Okay, let's go on to this one. What's the name for this? 12D. tetrachloro, ethylene diamine, chromate 3. That's correct. Tetrachloro, ethylene diamine 3. So I could write that up here. Tetrachloro, ethylene diamine. Usually ethylene diamine is put in parentheses because we don't want it to be confused. We don't want people to think we have one ethylene and 2 amines. Right? Separate. Yeah, because this one looks like 3 ligands. 1 ethylene ligand and 2 amine ligands, right? Although you know the spelling difference, but you can see the spelling's inconsistent. So tetrachloro, ethylene diamine, what? Chromate 3. That would be correct. Okay, let's go on to the next one here, which is 12E. Yes, that's correct. Tris ethylene diamine chromium 3. And so how would you spell that out? Tris, because the ethylene diamine contains a prefix, number prefix. Tris ethylene diamine chromium 3. Now, tris ethylene diamine chromium 3, is that a 3 coordinate? No, ethylene diamine is a bidentate ligand. And so when we think about this, this is actually going to be an octahedral complex. Because we got 3 ethylene diamines, each of those bite in 2 places as a bidentate ligand. And so actually there are going to be 6 bonded atoms to chromium, which gives us a what we call a coordination number of 6. What's the coordination number of chromium in this one? We have 4 chloros, which are monodentate, and 1 ethylene diamine, which is bidentate, so that's a total of 6 atoms bonded. So this would be 6 coordinate. This would also be 6 coordinate. 2 chloros, but also 2 ethylene diamines, so a total of 6. This chromium, so it looks like chromium likes to form 6 coordinate complexes. All these are 6 coordinate complexes. Here. Chromium and plus 3 oxidations. Okay, let's look at 14. Why don't you name that one here? Number 14. Okay, does somebody have it? This is an ionic compound consisting of a cation and an anion.
The first part, is it tris ethylene diamine cobalto or no?
Cobaltate.
Cobaltate. Why is it cobaltate instead of cobalto?
Cobalto. Well, it's neither of those. Cobalto is wrong because the O ending just goes for ligands, never the central metal. And only anion ligands at that. And so the O ending is just for ligands, anion ligands. Cobaltate is wrong because this is a cation. How do I know it's a cation? Because cations are always written first. In a formula. If this is an ionic compound, so it's got a complex cation and a complex anion. And so trisethylene diamine, that's fine. We did that just now. Trisethylene diamine. But the name of the metal should be cobalt. And the charge can either be +2 or +3. Is it +2? Okay, what we have to do is, if cobalt is +2, then what would that make chromium? And so ethylene diamine is neutral, so this is +2. The whole cation must be +2. And that means the whole anion must be -2, because it's a 1-to-1 ratio. And so in order to make this -2, it's got to be -2 times 3 is -6. -6 plus what gives us -2? It's got to be +4. So is +4 a common charge for chromium? No, +4 is not. The common charges for chromium are +2 and +3. And so cobalt cannot be +2 in this. Cobalt must be +3, yeah. And so this is going to be cobalt 3. And then the anion name is going to be trioxalato. Now look at the difference here. Do we really need parentheses? No, parentheses aren't really necessary, so we'll just have trioxalato because there's no confusion here at all. Trioxalato, chromate 3. And so now this is an anion ligand, so we have to use chromate. And then it's got to be a +3 charge, because +3 minus 6 will give us -3, which will balance out the +3 of the cation. So this is the compound name here. I might have screwed up the homework assignment because I might have put in some structural problems on the homework. So take a look at the homework and just do the nomenclature problem for chapter 24. The structural stuff is going to come later. Isomers. I think I put a couple of isomer problems in there, now that I think back. And it's too early. I'm not going to talk about isomers yet. I'll talk about isomers later. All right, that's writing the name. Now let's go in the opposite direction. So once you're comfortable writing the name, we want to get comfortable writing the formula for these things. And so let's take a look at the formulas. Next. So we're going to do number 4 here. Now, when we look at the first name, 4A, you can see it's potassium space hexacyanoferrate. So this potassium space, this must be the cation, potassium. Potassium ions are easy, right, because they aren't complex cations, they're just your standard potassium ion. And so potassium ions are K, and the charge is plus. Now we have hexacyanoferrate 3 as the anion. So the anion is a complex anion, so we'll have a square bracket here. Now, what do we write first? Do we write the hexacyano first, or the ferrate first? The ferrate. It's opposite order from the name. That is metal ligand, whereas name is ligand metal. And so iron, and then hexacyano is, we only have one type of ligand, so it's easy. We don't have to worry about ordering this. It's going to be CN, which is cyanide, 6. Cyanide is the ligand, is cyano. Each cyanide is -1, was -6. Iron is what? +3. So -6 plus 3 gives us -3. And so we'll need 3 potassiums to balance out the charge. So it's going to be K3FeCN6. Potassium hexacyanoferrate. 3. All right, let's go to 4B. 4B is bis ethylene diamine copper 2 ion. All right, we're just dealing with a single ion, a complex ion, so square bracket here. Now, bis ethylene diamine copper 2. What goes first, the ethylene diamines or the copper 2? Copper. We got to flip the order, right? And so it's copper.
Copper, parentheses, EN, parentheses, 2, and then bracket 3 plus 3.
Yeah, 2 plus is correct. Ethylene diamines are neutral. Okay, so it's going to be copper. So this would be bis ethylene diamine copper 2 ion. It's a cation. Let's go to 4C. Penta aqua hydroxo aluminum 3 chloride. Well, yeah, whenever we see a space like this, then we're separating the cation from anion. And so this must be the cation here, and chloride's the anion. So chloride anion is simple enough. We could write that now. Chloride we know is Cl minus. But what is the cation? So let's figure out the cation. It would be bracket, and then penta aqua hydroxo aluminum 3. So we'd start off with Al, aluminum. And then we have to figure out, do we write the aqua first, or do we write the hydroxo first? The hydroxo comes first, and the reason it comes first is it's an anion, you know. Anion. Anions come first. If we had more than one anion, we'd put them in alphabetical order. And so we have the hydroxo. Now we need the penta aqua. There are only 2 ligands here. And so we have a hydroxo, and then aqua is water. And we need 5 of those, penta aqua. And that completes it. And this is aluminum 3. And so the whole thing is going to be, what did you say, 2 plus? Yeah, that's correct. And so we'll need 2 chlorides to balance out the charge. And so this is just going to be AlOH. H2O, 5, Cl2. That would be the compound. It's an ionic compound. All right, let's go to the next one. D. Amine chloro bis ethylene diamine chromium 3 sulfate. Okay, again, there's a space here. The cation comes first, and then the anion. Well, let's do the anion first because it's straightforward. It's just the sulfate anion. So sulfate is SO4 2 minus. Now the cation is complex cation, so let's figure out what that is. Amine chloro bis ethylene diamine chromium 3. So what do I write first? Chromium. Chromium comes first. And then what? Chloro, anion ligand, and then amine or ethylene diamine. Amine would come next, NH3, and then ethylene diamine, which we can abbreviate EN. 2. All right, here's where you're going to see a difference. If you check the answers, the solutions guide, if you check the solutions guide, the En is written before NH3. Why? Because they alphabetized it according to a formula. So N versus E comes first. So that's what they did. But you could ignore it if you want. What's the total net charge on this? So chromium is +3. Chloro is -1. This is neutral. So +3 minus 1 is +2. And so this is 1 to 1. So the formula is going to be CrCl NH3 En 2 SO4. If there starts to be some blending, you know, Cl into NH3, you want to keep those separate, you could use more parentheses. So for example, you don't know if this is a Cl NH3 ion or what. Or we can leave it on. All right, 4E is an example of a complex cation and a complex anion. The cation name is tris ethylene diamine iron 3. The anion name is hexacyanylferrate 2. There's a space between the cation and the anion. You can see. So let's go ahead and do a 4E here, which is, let's write the cation first. So what's the formula for the cation? Fe En3. 3 plus. What's the formula for the anion? FeCN6. All right, is this the right way to write CN? No, we need the parentheses here, otherwise it looks like I have 6 nitrogens and 1 carbon. So this would be 6. This is an error on one of the PowerPoints. And the charge? 3 minus. 3 plus 3 minus is 1 to 1. And so the formula would just be this: FeEn 3 Fe. Is it 4 minus? Oh, you're right. You're right, because this is iron 2. Iron 2, this has got to be 4 minus. So it's not so simple. But what we can do is we can do this, you know, the cross multiply thing. Right? And so we need 4 of the cations and 3 of the anions to balance out the charge. All right, are you okay so far with those? See.
Is there exam on Tuesday going to cover nomenclatures, or is it just
No,
like the reactions?
only the chemical reactions. That's it. So just focus on those. Nomenclature we could have on another day, like Thursday, you know, something like that. Nomenclature would be a very short, like quiz kind of thing. All right, now we're going to drop back to chapter, well, 14 is officially the next, but we're going to skip 14 and go straight to 15. Unless are there any questions about nomenclature? Chapter 15 is titled Principles of Chemical Equilibrium. Now we're going to be talking about these partial reactions. You know, what's air made of? The air that you're breathing, what are the 2 major components? Nitrogen and oxygen. Is the nitrogen and oxygen in the air very reactive with each other? Does it form a stable mixture? Yeah, it's a stable mixture. However, nitrogen and oxygen can be forced to react. You know, they're in lightning bolts like this, there are high temperatures, which causes the nitrogen and the oxygen to become very, very excited. That is, very, very energetic and collide with enough energy to react to form NO. Also in automobile engines, you know, in automobile engines, air is being sucked into the engine itself. Not only the oxygen air you want to combust the gasoline, but at very high pressures and high temperatures, not only will the gasoline combust, but also the nitrogen will react. That is, get oxidized by oxygen. So it's like forcing nitrogen to burn in a way, because nitrogen would be the fuel. Okay. But do you think this reaction is complete? No. Even with a lightning bolt, very little nitrogen and oxygen actually react, right? Most of it stays unreacted. And even when we form NO, you know, actually in the video, you know, what they saw was when nitrates catch on fire, it produces NO. NO is a colorless gas. The NO is rapidly oxidized in air to NO2, which is the brown gas that you see in smog and nitrate fires. So we're going to be looking at these situations where the reactions don't go to completion. And the first reaction that we're going to look at is down here. Can you guys see this right at the very bottom? The slide. Let's see, bring that up. I don't know what happened to my scroll bars here. Well, sort of. It's like a problem with the page. Well, this morning I was well, anyway, I'll just write it down here. Well, let's take a look at this redox reaction here. A lot of redox reactions can be tricky to predict because of the conditions. The conditions can change things. So a lot of these, we just mix it and see what happens. And so if you take copper, 2 ions, you take 2 copper 2s plus a tin 2. One of the properties of tin 2 is usually known as a pretty good reducer. Reducers are electron rich or electron poor. Electron rich, but you're going tin 2, how can that be electron rich? It's got a 2 plus charge. Well, it turns out that tin 2 is fairly electron rich because it's a big ion and it's not too hard to take away more electrons from tin. And copper 2 can do that, but in this process, copper goes to copper 1 and tin goes to tin 4. And so tin 2 is usually a good reducer. Copper 2 ions are a decent oxidizer. And so we have this redox reaction occur. If we use the chart would have told us copper 2 goes to copper metal, not copper 2 goes to copper 1 ion. But like I said, different conditions can, you know, take you part way or all the way. You know, it depends on how it reacts. But in this particular case, it just took it part way to copper 1. And not all the way to copper metal. All right, it turns out that the reverse reaction is favorable as well. And to show that, we usually write 2 arrows like this, one going forward, one going reverse. But which one's more favored? And so what they did here in 15.2 is they're just showing the reverse reaction. They just rewrote it though. The reverse reaction is 2 copper 1s reacting with tin 4. The tin 4 is going to oxidize the copper to copper 2, and the tin 4 is going to be reduced to tin 2. And so this reaction can occur both ways. Here. If it can occur both ways in any significant degree, then we're going to have incomplete reaction. We just can't have complete reaction, because what's going to happen is this. As the forward reaction takes place, the concentration of products builds up. As the concentration of products builds up, their collisions become more frequent. As the collisions between the product species becomes more frequent, then the chances of a reverse reaction become higher. And so when we have reversible situations like this, then we reach some point where, you know, we can't exceed a certain concentration of product because of the reverse reaction becoming significant. And so this means we handle these differently than in Chem 1A. And so what I'm going to do is I'm going to do this like a Chem 1A problem. Chem 1A stoichiometry, we look for limiting reagents, excess reagents, right? Calculate theoretical yield, etc. And so we're going to go here. We're going to go to experiment 1. We're going to take some observations. We look at experiment 1. We're going to start off with 0.100 moles of copper 2, 0.100 moles of tin 2, 0 and 0 for the copper 1 and tin 4. And so what I'm going to do is I'm going to set this up as an ICE table, an ICE table. And so initial, I stands for initial. Initially we have 0.100 moles copper 2, 0.100 moles of tin 2, 0 moles of copper 1, and 0 moles of tin 4. Now in Chem 1A, you'd figure out what the limiting reagent is. Which one is the limiting reagent here? You just do it by sight. Is copper 2 the limiting reagent or tin? Well, different ways we can tell. It's a 2-to-1 ratio. So for every 1 tin, we need how many coppers? 2. So if we have 0.1 tin, we need 0.2 coppers. Do we have 0.2 coppers? No. We don't have enough copper. We have enough tin, plenty of tin. And so it turns out that copper 2 is the limiting reagent. What happens to the limiting reagent in a reaction? The limiting reagent is completely consumed, right? And so if the limiting reagent is completely consumed, how much of it do we lose? We lose all of it. And so the change, the C stands for change. The change is we're going to lose all the limiting reagent, and we're going to be left with no limiting reagent. The limiting reagent is completely consumed. So we get 0 moles. Well, how much of the excess reagent did we just consume? Well, we can do a bit of stoichiometry. In the context of the ICE table, the stoichiometry is easy. This is the way we do the stoichiometry. For every tin, we lose twice as much copper. So we'll call tin X. And so that means copper will be minus 2X. We call this minus 2X. And therefore, tin will be minus X. Because it's a 2-to-1 ratio. The 2 comes from the coefficient. 2, 1. Yeah. And so if 2x is 0.1, that means x is half that, or 0.05. So we're going to lose minus 0.0500 moles of that. And so we're going to be left over with 0.0500 moles of unreacted tin. So E stands for the end of reaction, or what we call equilibrium. And so I is the initial. C is the change, and E is the end, or equilibrium. And so at the end of this reaction, Chem 1A style, we'd expect to consume all the limiting reagent. Some excess reagent remains. How much excess reagent remains? 0.0500 moles. We started off with 0.100 moles. We consumed half of it. And how much product did we produce? Well, the product is going to be based on the limiting reagent here. And so this is going to be plus 2x. Well, 2x, we lost 2x here, 0.100. We're going to gain 2x here, so we're going to gain plus 0.100 moles. And so at the end, we're going to end up with 0.100 moles of copper. So all the copper 2 was converted into copper 1. So we started off with 0.100 moles of copper 2 and convert that all to 0.100 moles of copper 1. And then over here for the tin 4, we call this plus x here. And so x is half of that, so it's 0.0500 moles. And so we're going to end up theoretically producing 0.0500 moles of tin 4. And so this is the stoichiometry problem here. Doing it in moles is easier than doing it in grams or whatever. We don't have to do any conversions, but we expect a theoretical yield of 0.100 moles of copper 1, 0.0500 moles of tin 4. We've consumed all our limiting reagent, and we have a little bit of excess reagent left over. Okay, half of it. So this is Chem 1A stoichiometry, right? The normal way you do it. Done in an ICE table. Well, we do all our Chem 1B stoichiometry problems in an ICE table as well. And so let's take a look at this. Let's look at some of the data. The only thing that this is missing is the change. You know, they eliminated one row out of here. And so we have ICE. This, oops, what time are we going till? 25? Oh, I'm sorry, I wasn't looking at the time. So we'll continue this tomorrow. And so spend a little bit of time fixing your reactions, and then we'll be good.